Can sedimentary rocks be laid down very quickly? Yes. In fact, here's the interesting point. You have a hurricane on the east coast of the United States, and the surge of water, for example, Hurricane Andrew, not because it's named after me, but because it was well documented, in 1960, deposited on the shoreline of the east coast of the United States a sand layer 6 inches thick. One hurricane 6 inches thick. Within a matter of years subsequently, it had all been homogenised, disappeared, eroded, all the rest of it by ongoing processes. So in other words, first of all, you accumulated the layer rapidly, but to maintain the layer's integrity, it couldn't sit around for many years later without something else being buried on top of it, which also would have to be rapid. So do sedimentary rocks? Yes, they have to form rapidly, otherwise they wouldn't be preserved. And interestingly, we find features in sedimentary rocks that help us. We can also help us work out how quickly they formed. We can also replicate these processes in the laboratory. You can get a enormously long, thin glass tank, extend an aquarium, a home aquarium, and make it, 100 yards long, 100 metres long instead of just 1 metre long, and you get a water flow coming down with sediment. You can actually generate layers quickly, but also you can generate the features that you also see in the real world in the sedimentary layers. So, for example, in some sandstones, you've got the main horizontal layer like this that extends for hundreds and thousands of square miles. And within it, there's bands of sloping. The sand grains seem as though they're being stacked up in a sloping alignment. And everybody recognises this has to do with the sedimentation process. The normal way of looking at it is in a desert dune. When the sand gets blown by the wind, it gets heaped up, and as it moves forward, it cascades down the front to form a sloping front that advances. Now, if this gets covered up, you're going to get the sloping front preserved. And that's exactly what we see, except the same thing can happen underwater. We see it off the coast of in San Francisco Bay. We see it off Long Island Sound, and there's places around the European coast where the ocean currents move very rapidly. They can heat the sand up into sand waves, and it generates the same sort of process of advancing the sand with these sloping fronts, that if you bury them, they get preserved. But here's the interesting thing. We can replicate the same in the laboratory with blowing the sand and also washing the sand. And what do we find? There's a distinct difference in the slope between water-laid and wind-laid. In a wind, the angle will be 30 to 34 degrees. Underwater, it's 25 degrees or less. So when we go out and measure in our sedimentary rocks, and we see that in a sandstone, for example, in the western United States, the sand grains, these sloping angled beds, are at 25 degrees or less, it indicates that it was water deposition. And that layer extends over almost a million square kilometres. Huge expanse, and it was all underwater. So we find these indications, and we can actually, from experimental evidence, we can look at the height of the sand waves. What gets preserved in the sedimentary rock is about half the height of the sand wave. And we know what speed of water you need, because we can measure the water currents, say under the Golden Gate Bridge, that produce these sand waves, and in the laboratory with these flume, this sedimentation tank. So we can work out the height of the sand wave and the speed of the water. We can go then and look at the sandstone and look at what the height of the sand wave must have been and the water that flowed, and then we can calculate how quickly the sand must have been moved. And instead of thousands or millions of years, we're talking about days or weeks at the very most to distribute this sandstone layer all the way over a million square kilometres out there in the western United States. And the interesting thing is we see this multiplied on a global scale. It's not just there. Many people think, okay, we do an experiment where we get mud and sand and silt and put it in a glass jar, put a lid with water and a lid on it, shake it up and let it settle down. And the sand grains, they're heavier, they settle very quickly. The mud takes a long time to settle. So it's interesting, more than 50% of the rocks, sedimentary rocks, are particles that are mud-sized particles, whether it's lime mud or muddy mud, as most people think of mud. And therefore, the conventional geologists say, ha, a flood couldn't have done it. You need a long time for these fine particles to settle out in slow water. Well, it was just before Christmas in 2006. The results of some laboratory experiments up at the University of Indiana were published, and they used a circular sedimentation tank where they're able to accelerate the speed of the water and the speed of the grains. They call it a racetrack plume. You know, the grains going round and round and round. And they put in mud particles, and they discovered that instead of the particles settling individually, the particles, because clay has residual electrical charge around the edge of the particles clump together into sand-sized accumulations, and the mud actually settled at the speed of sand grains, and you could accumulate these mud layers very rapidly. So all of a sudden, like, their argument that over 50% of the rocks, sedimentary rocks, had to be deposited slowly, we can demonstrate that it had to be rapid. And like I told you before with the limestone, the chalk, even though it's fine-grained, the fossils in it indicate that they had to be rapidly buried, and that's multiplied. Many of the shales or mudstones have lots of fossils in them. Therefore, the fossils had to be buried rapidly. Therefore, the mud had to accumulate rapidly. And therefore, we have the evidence both in the field from observation, replicated in the laboratory, that sedimentary rocks all can be shown to form very rapidly. I can show you layers of conglomerate, which is boulders, all massed together and cemented by sand and silt, a layer 50 feet thick over 100,000 square miles. Where in the world today do we see something like that happening? Nowhere. The present can't be the key to the past, which is the philosophy behind all of modern science and modern geology. No, some extraordinary event picked up all that material and buried it rapidly, spread it rapidly over such a vast area, and then it was preserved to form that conglomerate bed. A rock layer can form very rapidly. If you go to the Caribbean and you get around Bermuda, for example, the ocean water is very limey because it's very warm, being in the tropics. And you got the sandy beaches. Beaches are actually made up of a lot of shell grit, in fact. And what happens is, of course, the tide comes in, and this very limey water gets left in between the grains of the beach. The beach stays wet when the tide goes out. What happens? Evaporation takes the water away and leaves the lime behind, and what do you get? You get beach rock. Between two high tides, the sand actually gets cemented into a rock-hard rock. It's like, we have to use the analogy of concrete. We mix up sand and gravel, but we put in a cement and water. The water helps spread the cement between all the sand grains. The water dries out, evaporates off, and the cement, there's a chemical reaction that binds all the sand grains and the pebbles together to make a rock-hard rock. And that's exactly what we see happening with sedimentary rocks. You can form it very rapidly. You know, a volcanic rock, it cools very rapidly, it crystallizes very rapidly. We've got evidence within granites that they even crystallize very rapidly. And we've even got evidence within metamorphic rocks that the transformation can happen very rapidly. So millions of years are not necessary to form hard rocks.